Welcome back, everybody. This is section 10.12 on buffers. So in this section, we would like you to be able to recognize pairs of substances that can function as an aqueous buffer system, and then write chemical equations describing the buffering actions of a conjugate acid-base pair, a buffer system. So let's first define what a buffer is. A buffer is an aqueous solution containing substances that prevent major changes in solution pH when a small amount of acid or base is added to it. So a buffer has to contain two active chemical species. It has to contain a substance to react with and remove any extra base that's added. So it has to have a proton donor, because if you're adding a little bit of base, like a little bit of hydroxide, you want something that's going to protonate the hydroxide to essentially neutralize it. And a buffer system also has to contain a substance to react with and remove any added acid. So a buffer system has to have something that can accept a proton, because if you add acid to a solution, you're generating more hydronium ions, more protons, and that could change the pH. So you need something that would accept the proton so that the pH doesn't change. And so the whole point of a buffer system is that if you want to maintain a pH at a certain value, like let's say you're working with human cells, they need to be maintained at pH 7.4. You would create a buffer system that's going to help maintain the pH at 7.4, so that if a little bit of acid is added to the system, there's something in the buffer system that's going to react with and neutralize the added acid, so the pH doesn't change. And if a little bit of base is added to your buffer system, there's something in the buffer system that can react with a little bit of base and neutralize that, so the pH doesn't change very much. So typically, buffer systems are comprised of a weak acid and the conjugate base of the weak acid. So oftentimes the conjugate base is present as a salt. For example, the conjugate base of the weak acid, carbonic acid, H2CO3, is bicarbonate, HCO3-, which when it's sold, when you're making a buffer system from reagents in the chemistry lab, we buy bicarbonate as sodium bicarbonate, NaHCO3. So this is the general diagram of a buffer reaction. It's an equilibrium reaction between a weak acid and the conjugate base of that weak acid. So you have HA, any old acid, in water in an equilibrium reaction where the weak acid can donate a proton to water to generate H3O+, and then you have the conjugate base of the weak acid left over. This is an equilibrium reaction, so it can go backwards. So H3O+ could donate a proton back to the conjugate base to reform the products, and it can go back and forth at the same time. Because the system contains a weak acid, if some base is added to the system, the weak acid, instead of protonating water, can protonate the base to make H2O. And so instead of changing the concentration of H3O+, which would change the pH, if a base is added, the weak acid will just protonate the base, turn it into neutral water, and the pH doesn't change very much. Similarly, if an acid is added, let's say you add some H+, the proton that ionizes off of an acid, if you add H+, it can react with A-, it can protonate the conjugate base. And so the concentration of H3O+ wouldn't end up changing very much. You'd protonate the conjugate base to make a little bit more of the weak acid and some water. And so the point with these systems is you want to maintain the concentration of H3O+. You don't want to be pushing equilibrium too far to the right to generate more H3O+, that would turn the solution acidic. And you don't want to push the equilibrium too far to the left, because if the concentration of H3O+ goes down, we know that means the concentration of OH- is going up, and we're making a more basic solution. So a buffer system will have something that can react with a little bit of base that's added, and it will have a component that can react with a little bit of acid that's added. So that the added base is neutralized, doesn't change the pH, as long as it can react with a little bit of weak acid that's in solution. Or if you add acid, there's a conjugate base in solution that will react with the acid again, to prevent the change in concentration of hydronium or hydroxide ions in the solution, which will mean the pH stays relatively stable. So these are some common buffer systems. Again, a buffer system, it needs something to react with a little bit of added acid, and it needs something to react with a little bit of added base. And so that's why buffer systems are always going to contain a weak acid and a conjugate base, because the weak acid can react with some added acid to neutralize it, some added base to neutralize it, and the conjugate base could react with some added acid to neutralize it. So these are some common acid conjugate base pairs. Acetic acid and its conjugate base acetate make a great buffer system. You have a weak acid that could react with some added base to neutralize it. You also have the conjugate base of acetic acid acetate, and this would react with any added acid to neutralize that. So the pH overall wouldn't change very much. Another common buffer system is dihydrogen phosphate, H2PO4- and HPO4 2- hydrogen phosphate. So here you have a weak acid. If base is added to this buffer system, this weak acid will neutralize the base, and the pH doesn't change overall very much. Or if acid is added to the buffer system, this conjugate base can react with the added acid to neutralize it, and again, the pH won't change very much overall. Our third really common type of buffer system is called the carbonic acid buffer system. Carbonic acid is our weak acid. So if any base is added, carbonic acid could protonate the base to neutralize it. The pH wouldn't change very much. And then the conjugate base of carbonic acid, -1 proton, is bicarbonate. So if any acid is added to the system, this conjugate base would react with the acid to neutralize that. And again, the pH wouldn't change very much overall. So let's talk about the acetic acid buffering system. It consists of acetic acid, that's our weak acid, and its conjugate base, acetate. So if we add a little bit of base to the solution, the weak acid will protonate the base, and overall, we're not going to change the concentration of hydronium ions, so the pH will stay stable. Or if we add a little bit of acid to the system, the conjugate base, acetate, can accept the proton from the added acid, and the overall concentration of H3O+ won't change very much, which means the pH won't change very much. Another example, this is the carbonic acid buffering system. You have carbonic acid, H2CO3, that's our weak acid. And bicarbonate, that's the conjugate base of carbonic acid. It differs by the removal of 1 proton, so it's the conjugate base. So if you add a small amount of acid, you add some H plus H plus. H plus is going to either react with water to generate more H3O+, which then would push the reaction to the left. This is an equilibrium reaction. So if you increase the concentration of one of the products, it's going to push the reaction to make more reactants. So the concentration of H3O+ when the reaction gets pushed to the left would go down. And so overall, it wouldn't change very much. If you added a small amount of base, the base would be protonated by one of the protons from carbonic acid to make H2O, and therefore the concentration of H3O+ wouldn't change. It wouldn't go up or down very much, which means the pH would stay relatively stable. So let's do a quick check. So which of the following pairs of substances could function as a buffer in aqueous solution? So the things you want to look for to identify substances that could function as a buffer is you want to look for a weak acid, and the conjugate base of the weak acid. So let's check if any of these qualify. So we have HCl and HF. So HCl is a strong acid and HF is a weak acid. So we don't have a weak acid and its conjugate base, so the answer can't be A. Next we have carbonic acid, H2CO3, and sodium bicarbonate. So sodium bicarbonate, it's an ionic compound that has a cation and an anion. So we know in solution it's going to be sodium plus HCO3 minus. And so between carbonic acid and sodium and bicarbonate, we have a weak acid and we have the conjugate base of that weak acid. Remember, conjugate bases are going to differ by removing one proton. So we have H2CO3 minus one proton gives us HCO3. So this is a weak acid and its conjugate base. So the answer is going to be B. But let's show why C also is incorrect. So in C, we have sodium carbonate and sodium bicarbonate. So this one's kind of tricky because you might think, well, there's a carbonate and a bicarbonate. Can't those function as an acid-base, a conjugate acid-conjugate base pair? But they don't differ by the addition of one proton. So you have sodium carbonate, so Na 2Na plus CO3 2 minus in equilibrium with Na plus HCO3 minus. So we don't have a conjugate acid-base pair here because we need a weak acid and then its conjugate base. And we don't have that available here. So it's not going to be answer C either. Okay, so let's go through an example describing a buffer system in action. So for the buffer system, nitrous acid, HNO3, or weak acid, and its conjugate base NO2 minus, the nitrite anion. Do the concentrations of nitrous acid and nitrite increase or decrease when a small amount of strong acid is added to the buffer system? So you want to start by writing the chemical equation for the buffer system. The buffer system is always going to consist of a weak acid plus water in equilibrium with the conjugate base of the acid and hydronium ion. And then we want to look at how adding H plus, a strong acid, would shift this equilibrium. Would it shift it to the left or would it shift it to the right? So here's our equation. We have nitrous acid, that's our weak acid, plus water, weak acid, right? It's like HA in our general equation, plus water is in equilibrium with the conjugate base of that weak acid. So that weak acid minus one proton. We're just going to label that Cb for conjugate base and hydronium ion. So if we add more strong acid, it's going to increase the concentration of H3O plus. When you add a strong acids completely ionize into H plus A minus. And so if you're generating more H plus, it's going to protonate water to make more H3O plus. So that's what adding a strong acid will do. We know from Le Chatelier's principle in chapter 9 that if we increase the concentration of a product in a chemical equilibrium reaction, we're going to push the reaction to the left because this is a stress on the system and the system's going to respond to get rid of that stress. So it's going to try to get rid of the extra H3O plus that we added to the system. So if we're trying to get rid of the extra H3O plus that we added to the system, that means that the equilibrium is going to shift to the left to get rid of that stress. So we're going to consume some of the conjugate base. It's going to react with the increased concentration of H3O plus to make water and nitrous acid. So we're going to decrease the concentration of nitrite. We're going to increase in concentration of nitrous acid and water. Nitrous acid is a weak acid, so it's not going to have much of an effect on the pH. And H3O plus concentration, because the equilibrium shifted left to account for adding more H3O plus, overall that concentration doesn't change very much because the buffer system can kind of absorb the added acid and convert it into water and a weak acid, so the pH doesn't change very much overall. So buffers are incredibly important for maintaining the narrow window of normal pH in blood. Normal blood pH is between 7.35 and 7.45. If your blood is more basic, the pH is higher, then you go into what's called alkalosis. And if it gets above 7.8, you can start to go into shock and die because your blood pH is too basic. If your blood pH is on the acidic side of things, it's lower than 7.35, what's called acidosis begins to happen, meaning your blood contains more protons or acid than it should. You can go into shock, and eventually if it gets below pH 7, you can die. So we're able to maintain this very narrow window of pH, range of pH in our blood, because we have buffers in our blood that help maintain the blood pH within this narrow range. Things like diet, metabolism, respiration, all those things can change the balance of hydronium ions in our blood, but because we have buffers in our blood, even if the concentration of hydronium ions goes up or goes down a little bit because of diet or metabolism, the blood buffers can usually buffer that small amount of change to make sure that our blood pH stays within the narrow range that keeps us healthy. So the blood buffer system is based on the carbonate buffering system, the carbonic acid carbonate buffering system. The other main buffers in our blood bodies are going to be different proteins and the phosphate buffering system. But in our blood, it's mostly the carbonic acid buffering system. And carbonate buffering in our system is directly related to respiration because CO2 from respiration combines with water to form carbonic acid. Carbonic acid is then soluble in our blood and then participates in the blood buffering system. So here's carbonic acid. Its conjugate base is bicarbonate. So these are both soluble in our blood systems. So when carbonic acid ionizes, it forms the conjugate base, bicarbonate, and hydronium ions. We can increase the concentration of carbonic acid in our bodies by altering the concentration of CO2. And we alter the concentrations of CO2 by our respiration rate. If you're breathing really fast, like hyperventilating and exhaling a lot of CO2, then your CO2 concentration is going to go down. And because these are all equilibrium reactions, if you remove one of the reactants, its concentration goes down, equilibrium will shift to the left, which means your blood pH will go down, or sorry, your pH will go up because you're going to reduce the concentration of hydronium ions because everything's going to shift to the left to make up for that decrease in CO2 concentration. If you hypoventilate, like you hold your breath, you're holding in CO2. And because you're holding in CO2, your CO2 concentration goes up. Let's just write a little arrow, right? If you hold your breath, your CO2 concentration goes up, you're not exhaling. So if this concentration goes up, the Chatelier's principle says that equilibrium is going to shift this way to get rid of this stress, this increased concentration of CO2. So if equilibrium shifts to the right, your concentration of H3O plus is going to end up going up. And if it keeps going up, you could enter the acidosis range of blood pH, eventually leading to shock and death. So CO2 is rapidly controlled by respiration. If you have a high rate of respiration called hyperventilating, you have a low concentration of CO2 due to increased exhalation of CO2. So if your CO2 concentration is low, Le Chatelier's principle says that everything's going to shift to the left to make up for that reduced concentration of CO2. And if everything's shifting to the left, that means your concentration of hydronium ions is going to go down. When your concentration of hydronium ions goes down, your pH goes up. So this could result in acidosis or alkalosis, which means you have a pH above the range it should be in blood. If you have low respiration, you're hypoventilating, CO2 is low. That's the one we just did. Sorry about that. If CO2 is high, equilibrium is going to be pushed the other way to get rid of the excess CO2, which means your H3O concentration goes up, which means your pH goes down, and you could suffer from acidosis because of your decreasing pH. So it's really cool, right? We have this blood buffering system to help prevent this. to be responsive to rapid changes in pH. Because if we suddenly start making a little bit more of this, again, Le Chatelier's principle kicks in and it's going to push the reaction back this way to get it back into balance. So again, a decrease in respiration will lead to an increase in CO2 concentration. Increase in CO2 is going to shift equilibrium to the right. We want to get rid of the stress, the excess CO2. So it's going to result in an increase in hydronium ion concentration in the blood. pH will decrease and you may suffer from acidosis. So CO2 concentration and H3O plus concentration always move in the same direction. If CO2 goes up, then hydronium ion concentration goes up, which means pH goes down. If hydronium ion concentration goes down, then CO2 will go down. So we've been talking about, like, if you change this side of the equation by changing your respiration rate, you can affect your blood pH. But your blood pH can trigger your body to exhale or inhale more rapidly or less rapidly to shift the equilibrium as needed to control the concentration of hydronium ions in your blood. It's one of the most rapid responses we have to controlling blood pH. So let's say you have a metabolism issue and your concentration of H3O is going up. You're suffering from acidosis. Some things that can be done is you can put bicarbonate into an IV. Bicarbonate will react with the excess H3O plus to get rid of it and neutralize your blood again. Or you can change your breathing rate. If you increase your respiration so that your concentration of CO2 goes down, then you could push this back this way and then decrease the excess concentration of H3O plus in your blood system. So we're going to watch a quick YouTube video that talks a little bit more about the bicarbonate buffer system, because especially with so many pre-nursing and pre-health science students in here, students interested in kinesiology and athletics, it's a really cool thing to kind of understand how your blood buffering system ties into your respiration rate, and they can work back and forth together as a rapid way to help you control your blood pH. All right, so let's check out this video about the blood buffer bicarbonate. That's the most important blood buffer in our bodies, and how it works and how it integrates with respiration.
Let's learn about the bicarbonate buffer system. Blood is maintained at a narrow range of pH, which is between 7.35 and 7.45. Serious problems result from blood that is too acidic or alkaline. Abnormal pH can lead to coma and death. One of the ways by which the body maintains the blood pH is through buffers. The most important buffer in the blood is the bicarbonate ion buffer. Before we see how it works, let's review a little bit about acids and bases. Acids are molecules that tend to give up hydrogen ions. For example, hydrochloric acid dissociates into hydrogen ions and chloride ions. As a solution's hydrogen ion concentration increases, its pH goes down, making the solution more acidic. Bases tend to combine with hydrogen ions, neutralizing them to form water. For example, sodium hydroxide dissociates into sodium and hydroxyl groups. The hydroxyl ion combines with the hydrogen ion, neutralizing it. As a solution's hydrogen ion concentration decreases, its pH goes up, making the solution more alkaline. If there are too many hydrogen ions, or an increase in hydrogen ion concentration in the blood, the bicarbonate ion combines with the hydrogen ion to form carbonic acid. If there are too few hydrogen ions, or a decrease in hydrogen ion concentration, carbonic acid dissociates into hydrogen ions and bicarbonate ions, thereby increasing the hydrogen ion concentration. We can use this equation to illustrate how an increase in hydrogen ion concentration, or acidosis, causes the reaction to move toward the left, which promotes the formation of carbonic acid. Likewise, a decrease in hydrogen ion concentration, or alkalosis, causes the reaction to move to the right, promoting the dissociation of carbonic acid into hydrogen and bicarbonate ions. In addition to buffer systems, the respiratory system also works to maintain pH. For example, if blood becomes too acidic, respiration rate increases in order to rid the body of carbon dioxide. A subsequent decrease in hydrogen ions occurs. Likewise, if blood becomes too alkaline, respiration rate decreases in order to increase the hydrogen ion concentration. You could say that hydrogen ion concentration follows carbon dioxide concentration. I hope you've learned something about the bicarbonate ion buffer, and see you next time.
All right, so I hope you enjoyed the video. That is the end of this section. We're going to talk about the Henderson-Hasselbalch equation next. It's a way to mathematically express buffer systems in terms of the concentrations of the weak acid and the conjugate base present. I'll see you then. Thanks.